In this video, we're going to have a look at improper integrals. So an improper integral can be one of two things. It can be an integral with an infinite limit, or an undefined limit. So let's give an example. So let's say we're finding the integral of 1 over x squared between infinity and 1 dx. So notice that it has an infinite limit, so that's that first type of improper integral. Therefore, it's undefined. So step one, in order to work this out in such a way that gets all the marks in an exam, first of all, we're going to replace the infinite or undefined limit with an unknown constant. So we're actually going to find the integral between a and 1 of 1 over x squared dx, which is relatively easy to do. So equals the integral between a and 1 of x to the power of minus 2 dx equals, well, add 1 to the power gives x to the minus 1, divide by the new power makes it negative, between a and 1 equals, and we're almost there, minus a to the minus 1 minus minus 1 to the minus 1 equals 1 minus 1 over a. So we've found the integral, but having replaced the infinite limit with an unknown constant. Next, we're going to let our unknown constant tend towards the original limit. So step 2, let a approach original limit and observe behavior of integral. So this really here is the key term that we're looking for. So we're going to let a approach infinity, and this problem term here, because we'd end up with 1 divided by infinity normally, which isn't possible. To divide anything by infinity isn't possible, because infinity isn't a number, it's just a concept about lack of limit. So as a approaches infinity, we'll see that 1 over a approaches 0. And we can just verify that by having a quick look at the function. So we've got the function of 1 over a, which looks like that. So as a approaches infinity, this gets closer and closer to 0. Therefore, the limit at infinity of 1 over a is 0. Therefore, the integral between a and 1 of 1 over x squared dx approaches 1 minus 0, which is clearly equal to 1. Therefore, we're done. But I have to stress that in an exam, you must show the whole limiting process here. Without it, you can't get the full marks. You must replace the infinite or undefined limit with a constant and show that constant approaching that limit. It's very important you do that, because as I say, you cannot get the marks in an exam if you don't do that. So just to wrap things up with this example here, I'm just going to introduce a bit of terminology. So when an integral that's improper actually has an answer, like it does here, the integral is said to be convergent. I.e. has a defined answer. Divergent is the opposite, i.e. does not have a defined answer. So I'm going to go through an example now of a divergent improper integral. So let's say we're going to do the integral between 1 and 0 of 1 over x dx. So notice here that the integral isn't defined at 0, so 1 over x isn't defined when x equals 0, so it's an improper integral. So now what we're going to do, we're going to do the integral between 1 and a of 1 over x, or x to the minus 1 dx. Now that's equal to log mod of x between 1 and a equals log 1 take log a. Well, log 1 is just 0 equals minus log a. Okay, so now looking at the limiting process, as a approaches 0, and for this it really helps to have a picture of the log graph. So here we've got the log graph. So as a approaches 0, log a approaches, we can see here, as log a approaches 0, as a approaches 0 rather, log a approaches negative infinity, which means that the integral doesn't have a defined value. Infinity isn't a defined value. Therefore, it's divergent. So there's no defined answer for this integral. And this one was also an interesting example of one where we've got a non-infinite limit, but the integral's still improper because the curve itself, 1 over x, is not defined when x equals 0. So we'll do one more example of such a curve. So let's have a look at this example here. The integral of e to the x over the root of e to the x minus 1 dx. Now this is a little bit more of a difficult example because it involves a substitution. We're going to let u equal e to the x minus 1. So I think it's going to be probably easier just to disregard the limits for now and do the integration without actually considering the limits. But before we start, I can see that just looking at this limit here, 0, that's going to cause the bottom to be 0. So e to the 0, take 1. The curve is undefined when x equals 0. Therefore, this integral, this limit here, is the limit that makes the integral improper. So let's have a go at it now. Let's do the integral without the limits. So let's just consider the integral of e to the x over root of e to the x minus 1 dx. So what we're going to do, we're going to let u equal e to the x minus 1, which means that du by dx equals e to the x, which means that dx equals 1 over e to the x du. So now subbing that in, which implies that the integral, is, so it's integral of e to the x over root u times 1 over e to the x du. We can see that the e to the x's cancel, which gives the integral of u to the minus 1/2 du equals, so u to the half, I'd want the power, divide by the new power, so divide by 1/2, which is the same as multiplying by 2, plus c, which is equal to 2 lots of e to the x take 1 to the power of 1/2 plus c. So that's that done. So we've got the answer to the actual integral now without limits. So now let's try and apply limits to it. So we want the limits to be log 2 and 0, but we noticed that when x equals 0, the denominator is e to the 0, i.e. 1, take 1, which is 0, so the curve's undefined. So this limit here makes the integral improper. So in such situations, we'll replace the improper limit with an a. So therefore, the integral between log 2 and a of e to the x over root of e to the x take 1 dx equals 2 e to the x take 1 to the power of a half between log 2 and a equals, so that becomes 2 and power of a half is a square root, so e to the log 2 is just 2, take 1 is 1, so 2 root 1, take 2 root of e to the a, take 1, which is equal to 2, take 2 root of e to the a, take 1. So we now need to think about showing the limiting process. So a replaced 0 because 0 made the integral improper. So as a approaches 0, we find that e to the a approaches 1, e to the 0 is 1. Therefore, the value of the integral I approaches 2 take 2 root of 1 minus 1, which is equal to simply 2. Now, a quick way of checking our answer is using a calculator. So if I just put the integral in the calculator, so I get e to the power of x over root of e to the x minus 1, and the upper limit was log 2 and the lower limit was 0. Now this isn't going to work as it is because the curve's undefined at 0, so let's just see what happens. Math error, as we expected. However, if we pick a number close to 0, 0.00000000001, and try and do it with that, let's see what happens. Now it should take a while, because it does take a while to calculate these integrals, because it's using the trapezium rule, I think, with a lot of strips. So quite a lot of calculations going on. But we'll just wait and see what happens. Well, this is awkward, isn't it? There we go. And it's very close to 2, which is what we expected. So we can't expect it to get exactly 2 because we're approximating it with 0.0000001. However, we can see we're in the right ballpark, so that gives us some comfort that our answer is correct. For more videos like this, subscribe to our YouTube channel, and to find out more about our Skype tuition and revision courses, go to alevelmathsrevision.com.